Okay, number 58 in chapter 10, definitely the hardest one for this chapter. What we have is a gas inside this cylinder, and it's initially at a temperature of 20 degrees Celsius. And what else are we given? We're given the initial pressure. The initial pressure is 1 atmosphere. The initial volume is 5 liters. Now here's what happens, guys. Here's what happens. They tell us that the temperature of the gas is increased from 20 degrees Celsius to 250. Okay? So that causes the gas to expand. Now they told us that the starting pressure of this gas was 1 atmosphere. Okay? Now when the temperature of the gas goes up, will that pressure change? Will the pressure of the gas change? Well, the answer is yes, but the reason is because there's this spring sitting here above the gas, right? We have this movable piston that can slide up and down without friction. But here's the thing you got to realize. If this spring were not here, if you removed that spring and then increased the temperature of the gas, would the pressure change with the increase in temperature? It would not. All that would happen is, this piston would go up, but there's nothing pushing back against it. You know what I'm saying? There'd be nothing pushing back against the piston to increase the pressure. So here's what we do. We're going to set this up. Initial, final. The spring constant of the spring is 2,000 newtons per meter. What else do we have? The area of the piston is 0.01 meters squared. So let's keep track of our data. Initial, and then over here we're going to put final. Okay, so starting temperature, we'll call it T1, is 20 degrees Celsius, which you want to put in Kelvin for all gas problems. Transfer that, convert that to Kelvin, so that's 293 Kelvin. Just add 273. Starting pressure is 1 atmosphere, and the starting volume is 5 liters. Now, we need to make this problem metric. Like, notice they give us the area of the piston in meter squared, and notice that the spring constant uses Newton per meter. So we need to make this data here metric. So 1 atmosphere, is that metric? What's the metric unit for pressure? Pascal. 1 atmosphere is 101,300 pascals. Liters is not metric. We got to convert that to cubic meter. The conversion there, 1 cubic meter is 1,000 liters. So 5 liters is 0.005 cubic meter. Okay, so this is our initial data. Now let's look at our final data. So what happens is the temperature rises to 250 degrees Celsius, which we want to put into Kelvin, and that is 523. And then P2 and V2, volume final. Now, what is the final pressure going to be? So when the temperature rises, the gas is going to be pushing into this spring. The spring is going to be exerting a force back, right? So the force of the spring is causing the increase in pressure. Remember what I said? If there was no spring here at all, if this spring were not there, would the pressure of the gas change? Nope. The pressure of the gas would stay the same. So the spring exerts a force on the gas. Now what's the definition of pressure? The definition of pressure is force over area. So the force of the spring causes a pressure which is going to be equal to force of spring divided by area. You guys follow me? Now what's the equation for force of spring? Force of spring is equal to Kx. You learned that way back in first semester. But here they're not using the term x. Here, what's the distance in terms of? H. So we're going to say Force of spring equals KH. Same thing as KX. So the pressure is going to be KH over A. Is that the final pressure or the increase in pressure? That's the increase in pressure. So P2 is going to be equal to P1 plus the increase in pressure. Right? So P1 was 101,300. So we'll put it in. So we have 101,300 plus the increase in pressure, which is KH over A. That's the pressure of the spring acting on the gas. All right, now let's look at volume. What is V2 going to be? Well, V1 was this shaded area right here, right? That's where the piston started. V2 is this whole thing. So what can we say about V2? V2 is going to equal V1 plus the increase in volume. Okay? Are you guys following this? Okay, so V1, thanks. V1 was 0.005 cubic meters. Now, what's the increase in the volume? The increase in the volume is this shaded area up here. That's the increase. So what's the equation for that? Well, we have the area of the piston and we have the vertical height that it moved. So the increase is going to be A times H, right? So what I've done so far is the hardest part of the problem. Now we need a gas law that will allow us to solve for H, which is what we're looking for. Okay? So what you do, you write out PV equals nRT, and you identify what stays constant from condition 1 to condition 2. The only thing that stays constant from condition 1 to condition 2 is moles and R. R is always constant. It's the gas constant. Okay, so now everything circled goes to one side, everything not circled goes to the other. So you end up getting PV over T as your constant here, right? PV over T equals NR. If NR is constant, then so is PV over T. Okay, so what we say is P1 V1 over T1 equals P2 V2 over T2. And then we plug into this, and you're going to see the only thing missing is H. All right, so we plug in here. So P1 is 101,300. V1 is 0.005. T1 is 293. P2 is 101,300 plus KH over A. And then V2 is 0.005 cubic meter plus AH. And then T2 is 523. All right, I'm not going to bore you with all the algebra, but just check this out. The only thing we don't have in this equation is H. And it appears in two spots. We got H right here, and we got H right there. So you got to do the algebra. You are going to get a quadratic, unfortunately. H comes out as 0.169 meters, which is the same as 16.9 centimeters. That is a tough problem. What makes it tough? The thing that makes it tough is realizing what P2 is and V2. Figuring out what to say about those. P2 equals the starting pressure plus the increase in pressure. V2 equals the starting volume plus the increase in volume.